Welcome everyone to the 8th week of our higher categories reading seminar. So today's speaker is Heiko from University of Bonn. I will be speaking about the Joyal model structure. Take it away.
Yeah. So we begin this with the motivation of the Joyal's lifting theorem. So I have a few reminders of what happened in the last talks up until now. So I don't know whether one can see myself, but I have to put this like this. So probably you can't really see, but whatever. Okay, you're right. So these are a few reminders. Kant complex is just something that is a Kant vibration to the terminal simplicial set. Quasi-category has all the fillers for the inner horns, and right-left vibration means that we have fillers for right and left horns. And when we do have this, then again, we have this notion of the homotopic category of some quasi-category. And what we do there is we just interpret the edges really as morphisms. And two edges, F and G, are identified. When such a situation like here happens, then that one something like this degenerate identity edges makes up a triangle with F and G, then F and G shall be identified. And we can make it into a category by the composition rule that says that we take any lift that exists in such a horn. This is an inner horn, 2-1 horn to be explicit, so it can be lifted by some sigma, and then this edge will be the composition. And using that, we can define what is an isomorphism in such a quasi-category. That is, it shall just be an isomorphism in this homotopic category. Whatever. Well, and then when we have a right vibration between quasi-categories like this, then any isomorphism that starts at P of X and goes to some Y, where P of X is the image of a vertex from top, from X, and now lives in Y, and so the domain is in the image, then this isomorphism lifts to an isomorphism in X. Okay, I didn't say it here. Lifts to an isomorphism in X. So this is the notion of isovibration in fact. So the statement here could be equivalently phrased as right vibrations are isovibrations.
Yeah, excuse me. Yeah, sorry to interrupt. Yeah, can you please change the color with like something lighter? That'll be easier to see.
Yes, sure. Maybe this. I just should be better. Yeah. Isovibrations. Okay, and what is an isovibration? I didn't tell this. Let me say this again, and let's do it here. So isovibration means this is inner vibration plus this condition. So from here to here, that any isomorphism lifts to X. when the isomorphism starts in some P of X. You can, in theory, also look at the dual version. So, for example, you could take alternatively the condition that you start in some X, and then you assume that goes to here P of Y, and maybe then it still works. And essentially, these two definitions are equivalent. Maybe we can see later why they're equivalent. But let's first prove the lemma that if it is a right vibration, then it is also an isovibration. So the idea behind this lemma, the proof of this lemma, is we want to find an inverse of a lift to the top. So when we have this diagram here, then this is actually lambda 1 0. Wait, no, it is the first one. Sorry. This. Yeah. So when we take this, then phi minus 1, which is an isomorphism, so we can form the inverse. This shall have a lift by definition of the right vibration. And then one can check that actually this gives an isomorphism that lifts to phi. And the reason for this, we have to find a few more lifting problems and lift them all. And if we do it all, then we get some edges, and the compositions are become the identity always. So essentially, we only need to consider these problems like that lift like this. Sorry, wrong direction. So here and here, and whenever we have here the identity and here some f, then it means that filling this horn, we get some inverse G, such that GF is identity or identified in the homotopy category. And this means that we can always find left inverses. And when we defined a left inverse of a left inverse, then we again get something that is equivalent to the original one, because inverses are unique. These are a few things that we probably did, but it is not too important not to see the details. I think just remember that right vibrations actually satisfy this condition that we can lift as every edge which starts one at px and goes to some other y, or also this condition on the other side. You can also phrase this alternative condition as the lemma that if P is an isovibration, then the dual P up, which goes from the x up to y up, is also an isovibration. Okay. Are there questions about here? Well, then let's continue. Let's do the join. So what is important for my talk will be mostly about Joyal's lifting theorem. This will come later in the middle of the talk. I will state the theorem, and it is an important part of the theory, how to give condition when we can lift certain horns. And in the proof, it will be important. An important technique is the so-called join. And what is the join? It is a monoidal structure on the augmented simplex category in this version here. So we have delta plus. This shall be the finite ordinals, as well as the empty ordinal, so 0. Considered as subcategories, considered always as posets and as categories. And we have some monoidal structure on this. m plus n shall be this guy, m plus 1 plus n. The unit object -1 is the empty set. And this is a monoidal structure on delta plus. So this simplex category plus an empty set, which is not always, which is not in delta, the usual delta, but we have plus now. And so this is a monoidal structure on there. And we get from this an induced monoidal structure on the augmented simplicial sets. So augmented simplicial sets, by definition, this is just the functor category of also the pre-sheaves on delta plus. I write it out, delta plus, comma set. Okay, and how we do it is we take one possible categorical construction would be to take the left Kahn extension in this diagram. But this is not the only construction. We can also do it explicitly, which is probably a bit more easy to see than how it looks like, and also why it's called the join. So let's do it now geometrically. So when we have two things like this part and this part, then the join topologically, we think of it as appending all the arrows in between, all the possible paths in between are now also contained in the join of those two. But because any map, for example, this one is essentially the composition of these maps, it suffices to just consider, to just draw this the single edge from the last of the first component to the first edge of the next component. So this gives the idea that when we take the ni, which is somehow the nerve of the interval I, and join it with the nerve of another interval, we get a longer interval, namely with now I plus 1 plus j of this size. And to make it explicit in formula, what are the n simplices of the join? It is this formula here. So the n simplices consist always of an n simplex on an I simplex in X. For example, to make it in this case, we could take a one simplex of this one here. It's a one simplex, and we can take here a zero simplex. And then we have 1 plus 1 plus 0. This is 2. So altogether, we get a 2 simplex. And what is the 2 simplex? It shall be this 2 simplex, which has these orientations. And yeah. So every combination of choosing simplices here gives together with the joining edges a simplex of the sum of the dimensions plus 1. And the phase maps are these ones. I will not go into the details why it works, but it just gives the usual things what we expect of the geometrical intuition of them. Similar for degeneracies. So I'm always interrupt when there are any questions. Yeah. So with this, we can now go to a little lemma on these joins. How does it look like? Yeah. So what we do here is we want to make a little push out here and check what it is. So we have commutative diagram like this, and we can take the push out in this part. The question, what will we get? And what we get is actually a horn, namely the kth horn in the corresponding dimension. So we already know that this here is exactly n plus 1 plus m simplex, and in there lives the kth horn, and this is what we get when we join them together. And to see this in an example, we can draw the pictures. For example, for let's say, where is the dimension exactly? N equals 1 and m equals, so both are equal 1. Let's do that. So for example, okay, k, what is k? Let's say k is 0. Then all together we will get the v simplex, because 1 plus 1 plus 1 is the v. So drawing the v simplex now. Okay, so this is what we get in the end. And the orientations are, use another color. It's this, this, and this. Okay, maybe it's a bit small. I have to draw it a bit bigger, but okay. Then what do we have here? Yeah, now m is 1, and this corresponds to this part, and that's this. And the 0 horn on the other side, this corresponds to this part, to this edge. And then we do the joinings. So it's here on the back and here. Similarly, on here, what we get is my pen does not always work as I want, but okay. On here we have now in blue this side, in red these two, and so the joining edges will consist of all these two, and the part in the back. So if you glue them together, then you apart from this side, everything apart from this. So this is the lambda dv 0 horn, because here we have, here we have the 0 edge. Okay, does this make sense? Any questions? Okay, now let's see what we do with this. When we have the joining with a fixed set t does not, simplicial set t does not commute with colimits, but it does commute with colimits when we consider it under the slice category under this set t which we join with. So we consider this this map here, this functor x goes to the canonical map that puts t into the second component after we joined with x there. Okay, and from this we just wish ourselves the right adjoint, and we call it underslice. So it looks like this, and then we calculated what it should be, and it turns out that here is the formula. The n simplices are just maps like this by the unit lemma, and we can now adjoin it to the other side. And now everything is known, and we take this as definition. It's similar process as when we look at the enriched internal HOMs and simplicial sets. So same idea. And now this actually is an adjoint because one can check that now this functor here, which is denoted here, it commutes with colimits, and then can prove that it is actually an adjoint. And we take this as definition and obtain the underslice, and also consider this with this part, and this is now called the overslice. Okay, now we have adjoints to the stuff, and from now we want to understand how the join and the slice work together with the very famous, always used lemma in homotopy theory, which is this here. So our key technical lemma, which we will use, is this adjunction. So whenever we have maps K to L, think of it as an inclusion, and S of T also, we should think of this as an inclusion, and some X to Y. Now this is usually a fibration, something like that. And then we have a correspondence in presence of this T to X, but this is just for the structure. We have a correspondence of lifting diagrams, of lifting problems of this form. So let's first understand what are the most difficult maps. This looks difficult, and this one. And both of these are induced by these two diagrams down below. How does it work? On top, we have here the push out of these things. So when we take here the push out, then we get an induced map because of the commuting diagram, which we always said here. This map, for example, is induced by S to T. This is induced by K to L, and so on. And then because it commutes, we get an induced map here, which is exactly the one that we take as I star I join J. And again, we have P slash J, P slice J. And this is induced similarly, but here we take pullback in this diagram and get, no, sorry, I get an induced map here, which is this one. Okay, and whenever we have this here, a note here that for this to work, we of course need a map T to X, and the left-hand side diagram, so here, this diagram here, lives actually in T in the slice category. And how does everything here lives under T? Well, we have this T, and it maps to this T here, and then goes to everything else by the maps and so on. And yeah, this is how this lives under T, and this is also the only possibility how we can even speak of the slice, because it is not, we have to have some map to X to make this, to make sense out of it. But yeah. Now we have it, and this is the what we do here. Okay, similarly, this lemma can also be dualized. So it is very similar, just taking not the underslice, but the overslice here. So these are now the overslices, just other way around. And again, to see how do these maps correspond to each other. For example, this map here, the lift, corresponds really exactly to this lift. By joining over this L join to the L slice on this side. So these are all the junctions working together. Okay. And from this, now I think we are able to state the main theorem, which shall be proved along its implications in this talk. And this is Joyal's lifting theorem. So when we have some quasi-category X, then there's a lift in this outer horn. So we have now the zeroth horn here, and we always can get the lift for the inner horns, but now it's an outer horn. And the question, when can we lift the outer horns? And the answer, it is possible if the edge defined by taking first delta 1, thinking of it as delta 0, no, delta one join the empty set, and then this goes via the functionality of empty set to this part here. It goes to delta one join partial, so the boundary of delta n minus 2, and then further it is included here into this latter part, the left hand right hand side, and by the combinatorial lemma we prove this was equivalent to the horn. And now we can take the map we have from the horn to X, and this all defines a one simplex in X. So this is from here to here is a one simplex in X. And the condition is this one simplex should be an isomorphism. And if it is, then we can lift this here. Okay, and we will first prove the theorem and then see what are the implications of it. So let's go to the proof. The proof will work in the following way. We have that when we apply the key technical lemma a few times, I will say in the next slides how exactly this is done. But we get from this these diagrams where both the top and the bottom part correspond to some special case of the key technical lemma from before. And we have that the blue maps here and here are right vibrations, as we will prove in a minute. And then we can show that this theta actually lifts to the top. Okay, let's see how these things are induced. This diagram here. So this is the upper part of the diagram. And it is just the special case, an instance of the diagram from the key technical lemma for the situation that S to T is actually this map, the inclusion of the boundary of delta n minus 2 into delta n minus 2, and Y being the terminal simplifier set, so delta 0. Okay. And similarly, the way this other thing is induced, so this was the top part here, and the bottom part is similar. This works as follows. We have again an instance of this diagram, but now for the inclusion of the empty set into delta n minus 2. So we can see, for example, why does it work? What we are doing here. This T is, of course, just replaced with this. So this is not a problem. And when we take Y empty set, then here we get the slice, what is happening? The slice over when Y is the empty set, then terminal simplifier set, then actually we get here also delta 0, and equally here. So doing the pullback along with the pullback with 2 delta zeros, this does not change anything. And when S is empty, then we can cancel it as well. So essentially, this is the reason why we get only the X. And similarly, for this situation, it's more or less the same, but now the S is just the boundary here. So everything as expected. Okay. And therefore, we have two instances of this diagram from the key technical lemma. And what we now need to prove is that this map is an isofibration, a right vibration, which will give us the lift. Okay. Now to see that this works out. So this is now again the situation. we have our an inner fibration P, and J as to T is some inclusion. Then P slice J here in this diagram is a right fibration. Note that it is important that S to T is an inclusion, as we will see in a minute. It does not work for some general sedation, but the corollary of this will then be that both of these two maps in the main proof are right fibrations, and we get the theorem from this. So to see that this map is a right fibration, we just test it along some inclusion like this, with some Horn inclusion, where 0 is less than k, smaller or equal to n, and consider any lifting problem of this form on the left-hand side. And using the key technical lemma, we can take all these stuff to the other side and find an equivalent lifting problem. So now we have gotten this. Note that this lifting problem now lives under T, because this is what we took to the other side. Okay, and then copy this diagram to the left-hand side again. And now we need to note that this lives under T, but well, it equally lives under delta N. So now we consider it to be under delta N, so in this slice category, and put everything back, but now with the over slice. So it's the dual version now. Okay, then again, copy it back. And now we need to get rid of the general monomorphism and just restrict our attention to only the inclusions of boundaries. But this is possible because the class of monomorphisms is the situation of the set of boundary inclusions. So to check such a lifting problem, it suffices to only consider the boundary inclusions here. And then again, when we have such a diagram, can put it back again by the key technical lemma to this version. And now what we have here is actually by the combinatorial lemma, the join, the Horn, the Kth n plus 1 plus m Horn. And now it has a lift because 0 is less than k less or equal to n. So this will be an inner Horn. It is obviously k is bigger than 0, and is also smaller than this one because of the plus 1 here. And plus m even makes it in general more bigger. Okay, so we have a lift because P is an inner fibration, and we have proven that well, we've proven Joyal's lifting theorem from this. So are there any questions? Okay, then let's continue. What we are doing now is a few corollaries from this statement. Namely, when we have a quasi-category X, then it is a Kahn complex if and only if its homotopy category is a group point. So T of X, tau of X is a group point. Tau of X is the homotopy category. Maybe I called it earlier. Sometimes it's called also H of X. There are different names of this, but well, okay, whatever. It is just the homotopy category from the first, from the second slide or something. So in essence, one can also say that quasi-category is a Kant complex if it is an infinity group point. This is why the name infinity group point comes into the picture. Yeah. And okay, the proof is the following. One direction, namely if it is a Kant complex, then it is an infinity group point. This is easy, just because we can look at horns like this. It's a 2-horn, and then we lift it and find inverses, and also in the other direction, so always possible. And the other direction follows by Joyal's lifting theorem. Namely, if it is a group point, then all the isomorphisms, all the edges are isomorphisms. So we can lift all the horns because the condition in Joyal's lifting theorem is trivially satisfied. And okay, we have to check explicitly the one-dimensional case. So this would be the situation where we have something like 0 here, taking it into delta 1, and then like that, we have to find a lift. But this is easy because we can just lift it to the identity on whatever vertex x this goes to here. So we can lift it to the identity of x as an edge, or once it flexes. Okay. Yeah, and this shows really why this I don't know, this makes it is an important corollary, maybe the most important corollary of the theorem. One could also call this corollary the lifting theorem of Joyal's is like more or less the most important implication of it. But we can make also other implications. For example, we could define the core of a quasi-category, which is analogous to the core, also the groupoid core of an ordinary one category. And how does this work? And we will see then how Joyal's lifting theorem comes in very handy to work with this. So when we have a quasi-category, then the core or the groupoid core, one also said groupoid core, X core should be the simplicial subset consisting of those simplices such that all the edges are isomorphisms. Okay, equivalently, we can say that this should be a pullback. So what are we doing here? We are taking the nerve of the homotopy category of X, and then we take here the nerve of the usual groupoid core of the homotopy category. So we essentially look at all those edges that are isomorphisms, and take the pullback from this. Okay, and in essence, this is just the same as this description on here, that we take all the simplices that have all the edges being isomorphisms. Okay, one can prove that X core is actually the biggest Kant complex contained in X. So whenever we have some morphism from a Kant complex, so as K is a Kant complex, then when it always factors uniquely over the core. Okay. Now let's see what we can do with this. We can characterize isomorphisms. So what is an isomorphism? We remember that it's just an invertible edge, but in usual category theory, an isomorphism is just an image of this category here. So we have the walking arrow category. So this is just the walking arrow. We can take a functor to this, put this, for example, into there, and then we added an inverse to this, and one could call this maybe the walking isomorphism category. And this guy is the arrow, so the functor category from this walking arrow to any category C. These are the isomorphisms of C. And when we take this functor category from this J to C, then these are the morphisms, and the below one are the isomorphisms of C. And the same will happen for quasi-categories, but we have to take the nerve of this J, and of course the nerve of this, and on top we have delta 1. So this would then be when we have some quasi-category, this would be the one simplices, and these are the isomorphisms. isomorphisms in the now infinity category C. To see this, we have to understand how this quasi-category, how this J works out and what the nerve actually is. And okay, we understand the nerve in the following way. For each dimension, we have exactly two non-degenerate simplices. Namely, we can start. So what are the simplices of a nerve? These are always paths, so strings of morphisms in the original category. And the non-degenerate ones are the ones that always go to a next one and do not stay at some edge. And here we go to the next one, go back, can go back and go back and so on, always alternating. And in this way, we can either start at 0 or at 1 and then must alternate to get it non-degenerate. And in this way, we have exactly two simplices. And a little remark here, actually, the realization of this, so the geometric realization of the nerve of J is actually the infinity sphere. So this is maybe interesting, and these two simplices here always give the lower and upper hemispheres in all the dimensions of the infinity sphere. So the usual cell complex, the cell complex structure. Okay, and also this gives the proof of S infinity being contractible because J is equivalent to the terminal category, and then nerve and realization preserve these natural transformations and send them to homotopies. But this is only a remark. We don't need this last point here in brackets for the theorem, which we want to prove, namely the characterization of the isomorphisms. Yeah, now let's do the proof of the characterization. And this works as follows. We can take this J category. We start with delta 1 and find a filtration like this. So we go to J1, J2, and so on, up until the last part, namely then it's Nj. And Jk is the simplicial subset generated by the K simplex, which alternates and starts at 0. So always one side of the sphere. And then one can check that from this we get push outs like this, that we have always some outer horns, which we do a push out with. And then we land in the end from Jk-1 to Jk. And now if this edge delta 1 to X is an isomorphism, it will factor through the core by definition. And because the core is a Kant complex by Joyal's splitting theorem, we have that it actually factors now also over Nj, which is what we want to prove. Okay. Are there any questions? Okay. Then what is also necessary or interesting thing, which is rather obvious in one category theory, is that the natural isomorphisms, so natural transformations that are isomorphisms, can be determined object-wise. So usually we just need to check that all the components of the natural transformations are isomorphisms, and then we can deduce that the whole natural transformation is invertible. And the question is whether this also holds in infinity categories. And yes, it also holds. Namely, we get the statement down here that we first define what are the object-wise invertible transformations. So Cisinski also writes K of X, Y for this set here. But I chose this fun core to make it explicit that it's somehow the object-wise transformations object-wise invertible transformations. And yeah, the definition of this is this pullback again. So we look at just the functor category, take a subset. This is a subset here, because this is a subset here. Here we take the core, but always restricted to only the objects. So there we are choosing only those morphisms which are object-wise isomorphisms, and then we take the pullback here, and we get essentially all the functors, we get always all the functors, and then all the natural transformations which are object-wise isomorphisms. Okay, yeah, again, we need this later. We define this Hx to be the simplicial set that satisfies this equality. In this way, this means here that the simplex of this H, so when we have some simplex, delta n to H, y, z in the situation, this corresponds to some map delta n cross y to z. And now this would be all the maps such that when we evaluate on zero on any vertex, so the constant parts, we stay constant on delta n and vary here. So when we vary here, all these isomorphisms. Stays in isomorphisms in in Z. And how does it correspond to the fun core? So the functors that are object-wise transformations, there it would be like the more or less the same situation, but we do not vary in y, but we vary in delta n. So it is the same. How can I write it? Just the same. Taking same idea. So when we take the fun core stuff instead, then it is when we vary here. Okay, and now, but what we really want is that for any quasi-category x and y, we have such an equality. This is what we want, namely the actual isomorphisms. So the isomorphisms, so those natural transformations that are contained in the biggest Kant complex in the functor category, are the object-wise transformations, object-wise isomorphism transformations that in here. One inclusion is obvious, namely this one. Whenever we have some invertible transformation, we can always evaluate, and then it will stay invertible. But the other one is interesting, and we prove it by proving that this is a Kant complex. So this is the proof. I first do the proof. So the obvious inclusion is the other one, and the non-obvious is this one, and it just suffices to show that this functor category is a Kant complex. This is because the biggest Kant complex is, of course, the biggest one, and so it will factor to it if we can show that the object-wise natural isomorphisms are a Kant complex. Okay, and actually it suffices to prove that it's a left Kant complex, because we can just apply a dualization and repeat the argument. So for the left Kant complex situation, we consider such a lifting problem where we need to lift against all these maps. And yeah, we want that there exists a lift into there. Okay, how do we do this? We first want to apply this adjunction to the other side and so on. So we make it in this way, that we take this auto diagram and join it to here. And actually now lifts from here to there correspond to lifts from here to there. And the question is, when do those lifts actually go also to here? This is what we really want. Okay. Now first, in the case that n equals 0, then actually the original problem is trivial, because what do we get then? Then we get here just the one edge. Here we get delta 0, delta 1, sorry. And there again, we can just take the identity on the chosen functor on top. So this map on top here, it just chooses a functor here, and we can take the identity and it lives in the object-wise isomorphisms. So this is not too difficult. But in the more general case, now we assume that n is bigger than 0, and we want a lift down below, but this works because there's a lemma, namely this evaluation at 1 is actually such a map that it lifts against all maps that induce bijections, all monomorphisms that induce bijections on objects. So here we have a monomorphism, and it is also bijective on objects. This is because n is bigger than 0. Otherwise, delta n and delta 0, the boundary and boundary of delta 0 would be empty. But now it contains all the objects. So this is bijective there. And in this case, we actually get a map, which is the content of the important lemma, which I skipped here. This is the statement: evaluation at 1 of this map has the right lifting property against monomorphisms that use bijections on objects. But we skip this first, maybe we have time later. But how do we get this map here? Okay, now we assume now we have gotten this map by the lemma, and the question is why does now the induced map on top also factor over this part? And we can see this from the next slide. So we have this lift L. Let's again write what is L. L lives here. So it goes from delta n cross delta n to the functor category x to y, as it is said here. And okay, yeah, this factors through the object-wise and isomorphisms, if and only if it hits just isomorphisms after we evaluate at any object x here. So when we evaluate, this looks like this. Yeah, we consider this diagram here, which is induced from this 0, this 1 comes from delta 1. The other parts come also from those things. For example, what is this? Here we have the second part, the second coordinate, and the x is just evaluation everywhere. Okay, and when we do that, let's see, we have that these two maps are isomorphisms because L restricted to delta 1 cross the boundary factors over the functor category, which has object-wise isomorphisms. And this is because of this being here, and yeah, then the map coming to there. So there are isomorphisms. Similarly, the bottom ones work as well, because now the first coordinate is 1, and there it factors the restriction to this part also factors over the functor category, and this is what lives here. Okay, and all in all, everything factors to there, and because now of 2 out of 3, we get that also the top ones are isomorphisms. Altogether, everything is an isomorphism here. So all the edges are isomorphisms, which means that 8 factors through this object-wise isomorphism functor category, which is what we want to prove. So what did we see now? We have shown that this is a Kant complex, this fun core, because we have shown that it's a left Kant complex, and this argument that we could dualize it and then also prove that it's a right complex. Okay, and all in all, yeah, this shows that the checking that something is an isomorphism actually works object-wise. And yeah, now the question is, do you want to see the proof of this, or the idea behind this lifting condition?
Yeah, I think you can just roughly sketch the.
Okay, then let's see. So I did not did not do it completely because of I suspected that the time is not perfect. We won't fit, but we have the following ideas behind this. So to prove that there's the right lifting property against the monomorphism that induced projections and objects, it suffices to show this for the boundary inclusions, but n is bigger than 0. And 0 is the only thing in these constructions where we get additional points. And so in this situation, we just get the projection objects when we consider only those ones. But again, if we consider this here as contained in the functor category delta 1, y, this again gives such a diagram here. But we have additional constraints, namely the part coming from delta 1 will be isomorphisms. In particular, delta 1 cross the last edge n is an isomorphism. So this here will hit an isomorphism in y when we restrict it to there. And this is useful because the way to prove it is we can get a lift in this diagram. So this lift here exists. We take this inclusion here, and it is known that this is a successive. We have to successively lift a few horns to get the lift there, and these are first a few inner horns, and at the last stage we have to lift an outer horn. And this is been done with can be done with Joyal's lifting theorem. Namely, the edge which has to be an isomorphism for its application is exactly this one defined by the last delta 1 cross last edge. So when this is an isomorphism, then we can lift the whole diagram. And in the end, we need to see that this lift here, which is here, so this lift should correspond to something that goes through here. And for this, it suffices to see that the lift lives here, because the one simplices of this object-wise transformation category are exactly the maps delta n to h delta 1 y. this delta 1 is the one simplices here, and H delta 1 says that this delta 1 will be invertible, which means that now when we consider as a map from delta n to y, then it is object-wise invertible transformation. So okay, if you consider as a transformation on a functor, on two functors between a delta n to y, then it's an object-wise transformation, invertible transformation. Yeah, and why does this hold? This comes from this diagram here being a pullback. Namely, why is it a pullback? The definition of this core is, when we go back, defined by restricting to the zero simplices and taking a pullback. And then you can use a pullback pasting to see that actually the diagram we see here is a pullback as well. And this means that our map that comes from somewhere like here, and so from this top map, which is already object-wise isomorphism, and the lift there, which are the same, they make up something that lives in here. And also when we put to everything the one simplices, this stays a pullback, and hence it gives our lift to the original problem, which actually lives in H delta 1, y. So this is the reason why the map has the lifting property against all these things. Yeah. Okay. And one remark I have to say, I did not talk really on the Joyal's model structure, on the Joyal model structure, because I thought it is a bit more coherent to see both of these explicit calculations together. And maybe we should talk next week about model structure together with the next two chapters, because they fit maybe a bit better with each other, in my opinion. Yeah. But if you have any questions, then yeah, ask them. And yeah.
So let's thank our speaker.
Yeah. My pleasure.
Let me stop the recording.